Hello, RustConf. How are we feeling tonight? Okay, so I have a couple of corrections that I need to make before we can continue. Some of you may have seen on the program that it says that this talk is about Tokio-Trace. That's a lie. This talk is not about Tokio-Trace. We renamed the library. It's called Tracing now. This happened after the conference materials and the programs and stuff were printed. So here's my first announcement of this. It's not called Tokio-Trace anymore. Also, it may have said in my speaker bio that I have 2 awful cats. I regret my statement. I only have 1 awful cat. I have 2 cats, but only one of them is awful. And I hope all of you got the joke with the title music, right? That this talk is about logging, and that was Kenny logging. Shout out to Adam Fultzer, who made that fun first. So this is a talk about tracing, not Tokio-Trace. Tracing is a set of libraries that provide a framework for adding scoped, structured, and async-aware diagnostics to Rust programs. So most of you are probably wondering, why am I the most important logging thought leader, right? So my name is Eliza Weisman. I'm a system software engineer at a company called Buoyant in San Francisco. We make Linkerd, the service mesh for cloud-native applications. I've been writing Rust since 2015. I've been doing it, I don't remember how long. I've been writing Rust since 2015. I've been doing it professionally for over 2 years. And I am a core contributor to the Tokyo, Tower, and Linkerd 2 open source projects. Some of you have probably also seen my Twitter where I make bad programming jokes and post pictures of my cats. Cool. So I guess the question really is, why did I make another logging library, right? We already have a pretty robust ecosystem in Rust around logging. There's the log crate, there's endlogger and Fern, and so on. So this is supposed to make my slide go. Oh, there we go. OK, so right. First of all, I don't like to call it logging. I like to call it GNU/logging. Cool. OK, so in my speaker notes, it says pause for laughter. And so I'm really glad that there was laughter. Yeah, so that was a joke. But I don't like to call it logging. I like to call it in-process tracing. And this is a big, very buzzword-sounding name. But we're going to talk a little bit more later about what that actually means. But to talk about the motivations for why I made another not logging library, I have to ask some questions to the audience. How many of you are using futures or now async-await? Show of hands. OK, that's a respectable number. And are you logging in those futures at all? And does this make sense? Do you get something out of this that's readable? Any of you? Not really? OK. Cool. That's about what I thought. Async is hard. There's supposed to be a pause for laughter here, but I guess you guys are just so sad about this that. But if you're writing any kind of high-performance network application or network library, you need to use some kind of asynchronous programming. But it presents some really unique challenges for diagnostics especially. When we're executing asynchronously, the execution of the program is multiplexed across different tasks. And when they require something from input-output or they require something from another task, instead of blocking the thread, those tasks yield, right? And then we start executing another task. And this is really good because it lets us use all of our CPU time, saturate the NIC, whatever the bottleneck is. But the problem is that because of this, we can no longer really rely on events happening in order. If we're logging in these asynchronous tasks, those log messages come out interleaved, or we see different contexts all logging information that might be very similar, and we can't easily trace what's going on between those log records by looking at the order in which they were displayed. So how do we get good, usable diagnostics from asynchronous systems? I'm going to touch on 3 what I see as the big pillars that we require if we want to have diagnostics in asynchronous systems that make sense. We need to capture context, causality, and we want some form of structure. So context. When we record that some event has occurred, we don't just need to know where it happened in the source code. which our existing logging tools are very good at. So they have like information about line numbers, modules, files, and that's all great. But it doesn't really tell us the runtime context in which some event that was recorded occurred in. So for example, if we have some HTTP server that's processing requests, that context might include things like, what client did this request come from? What were the request's HTTP method? What was its path? What were the headers on that request? And in synchronous code, so not async, we can infer that context by looking at log messages in order, right? If we see accepted request from this IP and then parsed a request with these headers after each other, then we know, oh, this is the IP that sent that request. But in async code, where we're switching between these multiplex tasks based on readiness of I/O and other resources, we switch between those contexts very rapidly, and we can't really rely on the ordering of log messages to determine context. Second, we care about causality. There's complex chains of cause and effect in these asynchronous systems. If I have some tasks that are running in the background, like a DNS lookup or a database connection or something, what caused them to start? What caused those tasks to perform certain work, and so on. We can't rely on log ordering to determine this kind of causality either, so we need to record it explicitly. Finally, it's helpful to have structured diagnostics. Traditional logging is based on human-readable textual messages. We prefer diagnostics, though, that are machine-readable so that we can interact with them programmatically. Sure, you can programmatically interact with unstructured logs if you use awk or grep, but it's not good. You know, if anyone uses tracing after this talk and you ever have to grep through a log again, you can come to my house and tell me this. I will give you $20. You can record typed data as typed values, and you can interact with that as typed data. So tracing. Tracing is a framework for instrumenting Rust programs with contextual, causal, and structured diagnostics. As I said before, it used to be called Tokio-Trace, but it's not called that anymore. Tracing is part of the Tokio project, so it's maintained by the people who brought you Tokio. It doesn't require the Tokio runtime, so you can use it in synchronous programs. You can use tracing in asynchronous programs that are using Tokio. You can use it in asynchronous programs that are using other runtimes. You can use it in WASM, probably. You can use it on bare metal with no standard, with some caveats. You know, ask me after class if this matters to you. So I'm going to take a minute here, and I'm going to switch gears. So we're going to look at a very quick demo. OK, so and in this demo, I am running a web server. And this web server implements an endpoint where you send HTTP requests, where the path of those requests is a single ASCII character. And then we implement something called character duplication as a service. We send you a response where the body of that response is that character duplicated a number of times equal to the received content length header. So you know, this is like very important that like because web scale, like we have to do this as a microservice, and this is absolutely mission critical, right? So, but we happen to know that we're experiencing an elevated error rate in this service. And so we're looking at these logs, and as you see, it's logging everything that's happening. And this is scrolling really fast. It's really hard to actually figure out what's going on here, even though we're recording all of this information. So we have very rich, verbose diagnostics. The example server is hooked up to a load generator that's just like feeding requests into it. And sometimes those requests are failing. So we're going to figure out why those requests are failing. Something we can do is that the example server, I've added a little admin endpoint where you can send a post request, and you can set a new filter that's used to reconfigure what tracing events are recorded. So what we can do is we can start out by curl -d, And if you're familiar with the nvlogger crate, you might recognize this syntax. We're going to look at the load generator only. OK, so we've dynamically reconfigured our diagnostics, so we're only looking at the load generator. And here we see that the contexts in which these events are occurring is being recorded with data about the request in which these errors are occurring. So we have our 400 errors, they're 404s, and we have our 500 errors. Looking at the 404s, we see that there's this request.path field. And for the 404s, it is just slash. And for the 500 errors, it is /z. And we can determine that, OK, the 404s are normal. The spec for this example app is that you send a path with a single ASCII character. The load generator is failing to do that, so the server is returning a 404. It's behaving correctly. But the 500s are worrying. So we want to look at the diagnostics from the server to figure out what's causing those 500s. And a very cool thing that we can do that you can't do with traditional unstructured logging is that if we go back to curl and we send a new request, and this request that we're going to send is going to be a little fancier. So this syntax is a superset of nvlogger's filtering syntax, right? Where you have these pairs of log targets and then verbosity levels. I don't call them log levels because this isn't logging, right? So we're going to introduce some new syntax now. We have these square brackets. And the square brackets indicate that we want to filter on a dynamic context. This is one of the things that you have to do when you're adding a superset of an existing syntax, is you have to add weird characters to it. There's an entire programming language that's called Objective-C. All right. So we're going to set this new filter. And the filter we're going to set is we care about field values, so these structured data on the span context in which events are occurring. And that's what the curly braces mean. We care about a field and its value. And specifically, what we want is the field req, or for request.path. And we want it to have the value /z. And you'll see I have to escape the quotes here because my terminal. But all I'm saying here is I want to see any request whose path was z. I want to see the context where that event is being handled, but I want to see all the diagnostics in that context. So I send that request. Look at that. So we're now seeing the entire lifespan of these requests, right? We see where the server is receiving the request. We see the headers there. Then we see that we're handling the request with a handler. And then we see this error that's being logged at a very high verbosity level, that I don't like this letter, and we're replying with a 500. OK, so we found the bug. It's not a good bug. I put it there on purpose. But you see here how we can trace the entire lifespan of this request, and we can only look at requests that match this filter. And even though this server is under really high load and lots of other stuff is going on here, we've cut out all of that noise, and we're looking only at these contexts that we care about. So that's a demo of the power of what we can do with this kind of structured diagnostics. I am going to go back now to my slides. Are we looking at the right slides? OK. And demo. All right. So how does this tracing thing, how does it actually work, right? You saw a cool demo. Everyone was wowed. We oohed and awed. How do we do this? What's actually happening here? What did I mean when I said in-process tracing? Are any of you familiar with distributed tracing technologies like open tracing, open telemetry, Zipkin, Jaeger? So these are diagnostic tools for distributed systems. Since I only see a couple of hands, I'm going to just explain very briefly. These tools are for diagnosing distributed systems. They are designed to allow you to track contexts as they move between nodes in a distributed system. So you have requests to one server that cause requests to another server. And the way this works is we propagate some headers. And those headers have an identifier that identifies a context called a span. And the insight behind the tracing crate, not tracing the concept, sorry, it's a dictionary word, I know that we can have collisions with these, is that asynchronous programs are kind of analogous to distributed systems, writ small, right? An asynchronous application in Rust has concurrently running tasks that are communicating through message passing. Message passing is asynchronous, it's fallible. So it's sort of like the network. I mean, the network is worse, right? It's even more asynchronous and it's even more fallible. But it's a similar concept. The only difference is that now everything is running in the same address space. So we can apply the same ideas that we use for tracing in distributed systems to tracing in asynchronous systems running in a single process. So we introduced some core primitives in tracing, and our core primitives are called spans and events. What are spans? A span represents a period of time in the execution of a program. It has a time when it starts and a time when it ends. So it's the time period between those 2 points. Spans also can be entered and exited in tracing independently from being created and ending. And we can enter and exit them multiple times. This is how we track the asynchronous execution that moves between task contexts. And a task might be executed within that context for a period of time. Then we yield, we execute some other task, we yield, we execute some other task. Right, and over the lifetime of a task, it might be entered multiple times. So we can record both how long the task existed for and how long it was being actively driven or executed. We also can separate between just the existence of this thing and when we're in the context of that work, right? Then here's how we make a span. We have this span macro. You get back this span object. And here we're creating a span called migrateSpan. Then we have an enter method on this span object, and that gives you back an RAII guard. So you can scope the entry of a span to a stack frame or inside of a scope in a function. And as long as you hold this guard, you are considered to be executing inside this span. When you drop the guard, you exit the span, right? We also have kind of a fun tool, which is this instrument procedural macro. It's an attribute that you can put on a function. And when you call that function, you create a span for that function. And it records all of the arguments to the function. And it works on async functions. And so async functions desugar right to a future that's driven when you await the return type from the async function. And so that return future is instrumented so that when we pull that future, we enter that span. When we stop pulling the future, we exit the span. And that span can persist as long as the future that is returned by the async function exists. Then we have a concept of events. Events are singular moments in time. And they're basically just, it's a log record. But it's more structured than a log record. We can add these structured fields to them. They're key value pairs. And tracing subscribers can consume these pairs as a subtype of Rust, or a subset of Rust primitives. So there are some primitives that we know about, like strings, integers, and so on. And you can interact with them as those types instead of as, oh, it's a string. Cool. I have a big string with a bunch of like stuff in it. Great, I can't deal with that. You need grep, right? So you don't need grep because we have structured fields of type values. And then we have this component called a subscriber. A subscriber is the interface for a component that collects trace data. It's basically like a logger, right? But you know, in the log crate, there's a log trait, and the log trait has like 2 methods on it. Subscriber has a few more methods because it does a lot more than a logger. But it's the same thing in that it's the main extension point for tracing, and it actually collects the data that's emitted. So libraries can provide subscriber implementations that do all kinds of different stuff, like recording metrics, printing logs to standard out, whatever. So how do we actually use this thing? Right? I'm going to work through a little example. This example is drawn from a very important domain, which is yak shaving. Some of you may have seen the version of this talk that I gave at a Rust meetup in San Francisco, where I had a slide much like this one. I've since been informed, I told you I had a few corrections to make. I've since been informed that the animal on that slide was a yak, or was not a yak, it was a cow. Google Images misled me. This animal is a yak. I have it on good authority. So I take feedback from anyone in the audience, and somebody told me this is not a yak. So I fixed it. Here's a real yak. So we're shaving some yaks, right? We're looping over some yaks and shaving them. But let's say we're shaving those yaks asynchronously, right? So this shave yak function is asynchronous. It's returning a future. It could be an async fn, or it could just be a function that returns a future. It doesn't really matter. So we're looping over these yaks. We're spawning a task to shave that yak. So we create this span called shaving yaks. This is where we're going to do all of the work of shaving these yaks. We can annotate it with whatever contextual information we want, like, say, number of yaks that we're shaving. And then we enter that span. That indicates we're executing in the context of shaving these yaks. And we have this enter guard that keeps us in that span. And then we loop over the yaks, OK, so then every time we iterate that loop for a new yak, we can create a span again. It's called shave here, and it records the current yak. And the shaving span is a child of this span where we're shaving all the yaks. So it inherits that context. So this span inherits the yak count from its parent, and it adds the span or the yak that's currently being shaved. So we have this instrument combinator. This attaches a span to a future. So whenever we pull this future that's shaving the yak, we enter that span. When we finish pulling it, we exit, right? And we can also put that on async blocks. So here now we're also recording an event after we finish shaving the yak. We call shave yak. We await the result. We debug, logging in the debug level that we shaved that yak. Return OK. We spawn this async block, and we instrument it with the span where we're shaving that yak. So again, this debug message inherits the yak that we're shaving, the current yak, and it inherits yak count, and so on. We have this tree of scopes in our program that represent the context in which we're executing. Finally, OK, so we can match on that, and we have either an error or we don't have an error. We record that there was an error, or we record that there wasn't an error. And we're recording this error as a structured value, so actually as an instance of the standard error type in the standard library. So we're not just printing it or formatting it to a string. The tracing subscriber can actually go, oh, this is an error. It's a dyn error. We can downcast it. We can look at its source. We can format it with debug. We can format it with display. When the standard library adds backtraces to errors, we can look at its backtrace, so on and so forth, right? It's actually a typed object. It's a Rust struct or a Rust trait object that we can interact with. Again, we don't need to record anything about what yak are we shaving, how many yaks are we shaving in these individual events, because they inherit that from the span context in which they occur. Great. So it also works very nicely with the log crate. One way in which it works nicely is that our macros are a superset of the log crate's macros. So if this compiles right, here I'm using log, and then I'm logging. If I want to switch to tracing in my application, right? Oh, sorry. Do you see the difference? Use log, use tracing. Same syntax. We have other syntax for doing more things, like creating these structured fields that log only just now has a concept of, but its macros don't. I'll get into that later. But you have a superset of log syntax. So if you want to migrate, you can just drop in tracing. And then you can go back and add more structured information, more spans, whatever. But it's very easy to adopt, and then you can incrementally roll it out. We also have adapters that let you record log records as tracing events, and tracing events as log records. So if you have a dependency that emits log records, you can record them as tracing events that are within that span hierarchy, even though the dependency doesn't know about tracing. Similarly, if you have a library that many people depend on, some of them are using tracing, some of them are using log. We have a feature that when you enable it, all of the tracing macros also emit log records. So your users who depend on log records being there will still have their log records. Finally, any runtime instrumentation has performance costs, right? You are doing something to record this data that you otherwise would not be doing. You can't get away from that. There's no such thing as a free lunch. But tracing's goal is to ensure that you only pay for what you eat. when, it's not a free lunch, but you don't have to pay for the whole lunch. You just pay for the parts that you want. We have tried really, really hard to design these APIs to ensure that there are no costs that you pay that you're not actually using. So what does that mean? First of all, when any instrumentation is disabled, like the filtering that we were doing in the demo, we've made sure that it's basically free to skip that. There's like one atomic load and a branch, so it's not free, but it's close. It's about the same cost as skipping a disabled log line in the log crate. We cache the evaluation of filters so that if you have like a regex that determines if something is enabled, you don't have to like run the regex over and over and over for the same thing. So we've optimized this a lot. We've also designed the subscriber API to ensure that you don't pay cost by default. So depending on the use case, a subscriber that's recording trace events might do a lot of different things. If you're doing time profiling, and there's a crate that does time profiling on top of tracing, you need to make syscalls to get timestamps. If you're logging with timestamps, you need to make syscalls to get timestamps. But if you don't need those timestamps, you don't need to make that syscall, right, to get that timestamp. If you want to track persistent data, you have to allocate. But if you don't need that persistent data, you don't have to allocate, right? And so tracing doesn't do any of those things. The subscriber can make the syscalls. The subscriber can allocate the storage if it needs to for the specific behavior that it implements. Tracing itself will never do those things. Finally, it's worth noting that we're really trying to bootstrap a whole ecosystem of libraries here. There are the core crates. There's tracing core and tracing, which are like the facade layer that you actually depend on that makes everything work. But on top of that, we have to actually implement these subscribers that have different behaviors. For example, we have a tracing format crate, which is what I was using in the demo, and it implements logging trace events to the console. But there's all kinds of other things you can do, like metrics or time profiling. John Gangset has a tracing timing crate that allows you to do like histograms of how long a span takes to execute, which I think is very cool. But there's a lot of other really neat stuff we can build to consume this unified layer of instrumentation to output any kind of diagnostics that we want. And there's a lot of stuff we can build using this, and I think I probably have only thought of like a tiny amount of it, so I'd really like to see what everyone else can come up with. So here's how you can get involved. It's on crates.io, all of the core crates are, and we have a GitHub repository in the Tokyo organization that has all of the like core tracing, and we also have a discussion group on Gitter and so on and so forth. So please, if you're interested, open a pull request or an issue. If there's something that you want to see, I love to get issues. I love feature requests. And if anyone actually wants to write those features, they can do that too. That would be great. But so please check it out, try it out, and we would love to hear from you. Here's some links. If you have any questions, reach out to me after class. Here's my email address and my Twitter, and you can get slides from my website, or I think they're on the RustConf website, so you don't have to like keep taking pictures like I see people keep doing. This is the only slide you need to take a picture of. I should have told you that at the beginning. There's a blog post I wrote on tracing that reproduces a lot of the same content from this talk, or please reach out to me whenever you like if you have any questions. Thanks.